Unfortunately, the organic crosslinkers, they can only work when the temperature is very high, above 90 degrees centigrade. So what about water production from zones that are low in temperature? We have in Qatar, for example, in offshore, we have in North Field, the temperature is about 40 or 50, maximum 60 degrees. So if you get such kind of organic crosslinkers, they will not form again. They need very high temperature. So, advantage of these organic and inorganic, they are stable, but as I mentioned, they need high temperature. The inorganic, they have problems of toxicity, especially the chromium escape, widely used. When we call this material the gel, we measure something called G prime rheology. This is elastic modulus. Once the elastic modulus is of the material, the G prime is higher than G prime, that means it is more solid than liquid, we call that one a gel. Why should we worry about this? When we inject these materials, it has to go through a long tube. And this tubing, we don't want any gel to form in, otherwise it will. So you have to know the kinetics of dilation very well. So that by the time you reach the target zone, you should reach that liquid. And then you isolate the zone, and the temperature of the reservoir will be the temperature. We don't want any formation of the gel, maybe more than one cell within the target zone, 1,000 meters, 2,000 meters. So you have to be very careful about the understanding the chemistry and the dilation mechanism. We don't want G prime to be like solid, because otherwise we cannot inject it. So the dilation mechanism should be studied quickly. Here I'm going to talk about it rheologically and thermal analysis. We can study this, what we call rheokinetics, or we can study the kinetics through thermal analysis and understand the mechanism, play with the formulation, delay the dilation sometimes using different chemicals, so play with the chemistry to avoid any dilation during injection. Of course, the gel and gel strength is affected by so many factors. Part of it is the concentration of polymer, salts, initial pH. pH is very important. Hydrolysis, the degree of hydrolysis, also is important. And all of these factors, of course, should be optimized to get the best kind of formulation for the specific application. So if you have a specific application, you have to know the target zone, what is the temperature of that zone, what is the water salinity, and so on, what is the depth, so that you can design the right formulation. So we study here in different parameters, and we develop the formulations. And actually, this work was done back a long time in Saudi Arabia, and the student was from Aramco. Directly after finishing his master, this work was applied in the field. And there was a success story that Muntashi, the one who my master student, he published this in SPE. They use this formulation. Of course, we did lots of calculation for specific depths. We use their field water to develop the formulation. At the end of the day, it was used in the field and stopped the water and increased. This is the gas reservoir. It has increased the gas reservoir, and the water has went down, as you can see from this. This is a field application of the developed formulation. Temperature and pressure also affects our study. Salinity is very important, especially salts work as retardants. Some of them like sodium chloride. Ammonium chloride is widely used to play with the dilation time. This, of course, work also. We tried in the lab in some high permeable rocks, and we injected these formulations, and then gave them some time, similar to what happened in the field, and then let them form again, and after that put water or any other fluid at very high pressure and see whether the fracture or whether the high permeable zones are sealed or not. And what you can see here on the right, the percentage of permeability reduction. Permeability has been reduced 2 hours, 5 hours, 1 day, 15 days, 94% in 15 days. This is in a sandstone with very high permeability, about I think 45 millidarcy. If you look at the carbonate, you see it about 145 days and still 99.7% sealing, so no water. So the gel was very efficient in sealing the fractions, which is very important. Here I try to add something for those who are not familiar with permeability. It is basically derived from every equation, fluid mechanics. We as chemical engineers will know this. In packets, that's the equation in the limiting case is basically for the laminar part of the area equation. It is applied later on we need enforcement. Polymer enforcement. Polymer enforcement is used a lot in the polymer science. Now we also enforcement for the gel. We use silica. We use silica by itself as well as silica functionalized with the cross-linker. So functionalized silica as well as silica. And what we can see here, major improvement when we use functionalized silica. And as I'll just show you here in this plot, how the strength, see the strength, G prime is the measure of strength. Palm PEI, the normal, when you add silica, non-silica plus PEI, or you add functionalized silica, major improvement. And here mainly the improvement is due to, we remove the mass transfer limitation. So it's basically chemical engineering issues that we're addressing in these problems, and they lead to this kind of improvement. Later on, what is important also contribution that we did we work a lot on cross-linkers, especially in organic cross-linkers. We developed this cross-linker aluminum acetate. We studied different types of aluminum. We moved from chromium to aluminum because it's more environment friendly, especially if you want to use it for offshore. And we found aluminum acetate is the best. You can play with pH and get different strength. Also, we did not just gels, but also sealing fractures. Sometimes when you drill, you create fractures. These fractures could lead to water getting out or draining fluid loss. Very expensive. So how can we use this formulations for sealing fractures? Yes. We use this, we create the largest fractures, different types of fractures, and we injected our materials, and it had a very excellent sealing properties. Now we are working on pre-formed gels. We form the gels outside, and then we inject them, and then they swell, and then they can go on with the fractures. This is an ongoing project. Of course, we are trying not to limit our application to what is called near wellbore, just close to the wellbore. See the fractures that are close to the drilling area. We want to go beyond down, what we call go to in-depth or to use it for diversion, or get our material to penetrate deeply in the reservoir, so that we can have better control for water. And this, we are trying to use these materials, pre-formed gels, and study their transport in this force field. That's why we are getting into computational fluid dynamics, to see how these kind of particles will change in the area, because they are swelling while they are getting in, so that they can fill the different fractions. I have a small thing here to show you what we are trying to do. To develop some materials of different sizes, so that it can go static zones and go deep in the reservoir, not just to close, and so that it can also freely see not just near wellbore, but also go down to the fractures, close to the tip of the fracture, because this is close to the tip of the fracture. Emulsified gels, we use them, but I will skip this part because we are running out of time. But also we develop emulsions. We use also nanonuclear materials as emulsifiers. In conclusion, it is very important to understand the chemistry. Lots of things here under the chemistry. Chemistry of dilation, impact of water, salinity, pH, so many things. So really understanding the chemistry of this material is very important. Polymeric gels will have different applications, either in situ or pre-formed. We can emulsify them, put them in emulsion, and we try this for specific applications. You have to design them according to the wear conditions, temperature, pressure, salinity, salts. You have to use the field water in that area because you use lots of water. So really the problem or the formulation should be tailored according to the area. I would like to acknowledge my research team here in Qatar, as well as also our university partners in one of the projects, as well as my former colleagues at King Fahd University and students who are now my friend and late Professor Shams from Saudi Aramco who passed away last year. The Islam is heading now the Aramco R&D in Houston, Abdullah Sultan, and Dean of Scientific Research at KPM, and Karsani, Nubel, Wyoming, and recently our colleagues in Missouri State University. So I'd like to thank all of them for their contribution to this work. Thank you.
I think we are running out of time. Maybe just we'll have one or two questions. So, Professor
بسم الله الرحمن الرحيم. المحاضرة الرئيسية الثانية will be for Professor Damia Barcelo. Professor Damia Barcelo is a full professor, permanent staff of in the Institute of Environmental Assessment and Water Research, Spanish National Research Council. From 2008 to date, Scientific Director of Institute for Water Research in Spain. أيضا he is a full professor chair in biology, College of Science, Kingswood University. أيضا he is honorary and guest professor of Xi'an University in China. Professor Damia supervised more than 64 PhD students. He has more than 1,373 publications and 226 books. His H index 152 and overall citation of about 70,853 and presentations in conferences more than 400. His lecture today, Professor Damia, you are welcome in our GISIC 09 in Jordan. And Professor Damia, he is the editor of Science of Total Environment, which is one of the leading journals in environmental research and studies. You have, Professor Damia, 20 minutes because we have a shortage in time. You have the word. Thank you very much.
Thank you, but thank you very much for the invitation and for the presentation. But I am not allowed to charge my presentation. You need to give me permission, otherwise I cannot. You cannot see anything. So the chairman of the Zoom should allow me to upload my presentation.
Upload presentation?
Yeah. Now, okay.
You can click on slideshow down there, Dr.
Yeah.
Sam. It's down there. It's down there, yes. Go down. Keep going.
Down?
Cancel this. Could you cancel this?
Yeah.
Go down to the bottom, to the right, and you could see the slideshow.
Notes, comments? Yeah, at the end. This one?
Yes, please.
Okay, thank you, sorry. Thank you very much for the help. So it's a pleasure for me to talk today. Sorry, I could not be here in Amman in Jordan. I've been there more than 10 years ago, but anyway, I hope I can come next time. I will try to be shorter. This is an overview of the work that we have been doing, not only on pharmaceuticals, but also on other chemicals. By the way, I will also talk briefly about one of the chemicals that we study in processed water recently for fracking. But also I will give you some hints or some ideas what we do on microplastics and also on the COVID, on the virus. This is a long collaboration with many groups, not only from Spain, but also other places like Mexico with microalgae technology. We have also collaboration with Khalifa University in Emirates, and also with other colleagues in Spain. Well, it's really an overview of a lot of things. So basically, what is the situation? We know that pollutants are there. We know the problems with the treatment plants. It's not easy to remove them. They have been estimated a lot of money that cost this, because in Europe, and especially in Europe, we have a very strict regulation on the pollutants. So to remove them from the treatment plants, it's a lot of money, and it's still things are going on, or improvements, because it's really very costly. These are some estimations how to remove ethylene estradiol in the UK. So it was millions of pounds to remove them. So this is just an example of what the situation. The situation is also globally. We look at the global world. We are now around 8 billion people. So we look at the situation, still more than 1 billion people is without water treatment or lacking appropriate treatment. And it's predicted that in the 2050, the situation will be worse, because there will be more people in developing countries, which will be born, newborns. And this will go up to 2.5 billion. So the improvement on the treatment plants is okay for the Western world, from developed countries, from the countries which are wealthy, but not for the rest of the world. So the situation needs a lot of effort for everybody. The situation in the treatment plants, my field is more pollutants. Although I work a lot with engineers, I have been working with engineers during many years. I am a chemist, but I am familiar with the engineers. So the situation is that in the sewage now you can find everything. So basically this is from Christian Doughton, a friend of mine in the US that now is retired. He talked about the mining of chemists, chemical information. We got all the information in the sewage, from pills, from everything everything goes to the toilet and everything goes to the treatment. And many times the treatment is incomplete, so we get this into the sewage. This is an example what rivers in Spain, for the 4 rivers that we did a study a few years ago, we are studying. More than 300 chemicals were measured, and you can see the impact of these sewage treatment plants in 4 different rivers. One of them is the Ebro, which is the largest, but the other ones are also important. So you can see different types of chemicals, pesticides, endocrine disruptors, pharmaceuticals. So there is always some chemicals in the river, and because of the treatment plants mainly. Also there is, of course, there is also the impact from agriculture, from pesticides from agriculture and runoffs, so non-point source pollution. The treatment plant is a key question, is a key factor, and the improvement of treatment plant is also very important. Most of the treatment plants are secondary treatment plants. This is what we did years ago in a study in the Ebro River, the largest in Spain, that we know that from the chemicals, the elimination is not the same. Even in the same river, the treatment facilities, they do not have the same hydraulic retention time, the same soil retention time. So the river itself, the plants are being built up by different companies, and the removal rate is different. So that makes the situation rather complex, not only in my country, it's everywhere. Usually the treatment plants are designed in different periods, different retention times, different zones. So this is the average elimination of several pollutants. You can see that some of them, they got very good elimination, like acetaminophen, paracetamol, widely used, but other chemicals like furosemide or diclofenac, they are not really eliminated, or the elimination changes from 20 to 80%. So it depends very much on the treatment plant. We had some chemicals like carbamazepine, which is an antiepileptic drug, which is not eliminated and is widely used around the world. Another problem that we have in the water is the antibiotic-resistant genes, and this is increasing in the last years. This is a study that we did here in Spain, in Girona, where we have the Institute of Water Institute. This is, you can see in this drawing, in this picture, the antibiotic-resistant genes going from the hospital, which is the largest one, the top one, and then going before the treatment plant and after the treatment plant and in the river. Although we eliminate quite a lot after the treatment plant, these are different periods. Although we are able to eliminate more than 50% of the antibiotic-resistant genes, there are still some traces in the river. The river still contains traces of antibiotic-resistant genes, and this is an increasing problem around the world, because we use not only the urban antibiotics for humans, we have also the animal, the farms. They use a lot of antibiotics. Another problem in the last years is the microplastics. Has been also a big problem in the treatment plants. We know they are there. and we know that need to be eliminated. I will give you a couple of slides later. And the recent problem, we are still under COVID. This is a work that we did in India, together with some colleagues there, on the levels of antibiotic resistant genes and in India, and how we could eliminate the COVID as well, the virus. Here, for instance, we see that in the different spots in India where the levels of SARS in wastewater, we are now in Europe and in US, in different countries, measuring also in the Emirates, measuring the SARS, the virus in the wastewater. We know that the virus is there, so the wastewater gives you a complementary measurement to the clinical studies, gives you data on asymptomatic people. But we found in India and also in other places in Europe that where they were the highest levels of virus in the wastewater, there was also a lot of antibiotic resistant genes. So the question is that because of the use of antibiotics, of course, when people are sick, they use more antibiotics. So basically, this is a big problem. So what I will be briefly talking here about different technologies, membrane technologies, and different types of membranes. You are familiar with them. Low pressure and high pressure membranes, eco-friendly technologies. We have been doing a lot of work with fungal biodegradation, also with microalgae, advanced oxidation, and then some applications to the hospital effluents because it's a hot spot. And then some examples of removal of the antibiotic resistant genes in a real plant using advanced oxidation, some examples on microplastics, and some examples also on the removal of SARS at the end. So if I have time, so I hope, otherwise I will go briefly. This is a pilot plan in the Catalan coast, in the Spanish coast, where we applied for the removal of pharmaceuticals. Here we can see this is the scheme of the plan, membrane and also reverse osmosis and nanofiltration. I will not go into detail. This information has been already published. If some of you are interested, you can just send me an email and you get the information. Basically, if you use reverse osmosis or nanofiltration, you can really remove most of them, 90% of the pharmaceuticals. This is not a problem. The problem may be the cost, energy cost, because when we evaluate technologies, we also need to consider the energy cost. In that particular case, nanofiltration is cheaper than reverse osmosis, as you know. So, but both of them, they can be used. Other examples are related to the algae-based technologies. We did this work together with our colleagues in Mexico, most of them also in other places as well, in Spain as well. So algae-based removal technologies are very much in fashion. They are being used. They have different applications, and this is one example of the bioreactors. We did a review paper. We did some examples on different mediums like Aspergillium maxima and Chlorella vulgaris in wastewater treatment. This is also with our colleagues in Mexico. And this is basically this is very important because the biomass, the use of microalgae is a friendly treatment, is an eco-friendly treatment, can be considered. The biomass, it can be used as well for biodiesel production, can be used also for different applications. So we have really a cheap way to do treatment. There are some advantages of these technologies, like very good removal rate of many parameters. We have also, you can reduce the CO2 capture. It has been now discussed how microalgae can also reduce the reduction of the CO2. So the advantage of this technology has been proven to be very, very efficient, and for all this removal of emerging contaminants, biogas production, and also all these aspects which can be really used. So the bioreactor, you can see here the scheme, how it works. So there's basically the different advantages, the biodiesel, and all kind of this. So we have been doing as well in Spain examples on this technology for removal of different pharmaceuticals, which is working pretty well, as you can see here. Sorry, and here. Why microalgae? Microalgae is why? Because they are ready to remove nutrients. Sorry, they can. Something is wrong with, now they can be used, loop energy loop, since the content of carbohydrates and oils allows them to be considered as potential feedstock for biofuels. They remove CO2 and they can be a powerful tool in the abatement of this gas. So this is something which is now also being explored. for the model of the circular bioeconomy model. This is different types. This is another example that we have been working with the Norwegian. By the way, as you know, Norwegian, they have fracking and oil industry, as well as linking with my first lecture, with the lecture of my the first lecture that we had today. And in this particular case, we have been working with them in the elimination of benzoalkonium chloride, which is a well-known anti-corrosion agent. We use it in fracking industry. And this technology of microalgae was able to eliminate more than 50% of this chemical, which is now a problem in most of the fracking operations. This is in application of different technologies. The hospital effluent is also a big problem because there are many different hospitals, many different treatment technologies. In fact, in Europe, this is a picture of Europe, there is not a unique technology used for treatment. There are many, many different and usually combined or hybrid technologies, membrane, oxidation, nanofiltration. These are some examples that we did in Spain on different technologies of like cytostatic compounds using ozonization in that particular case, which is very useful for the removal of cytostatic chemicals. Fungal treatment, we have been collaborating a lot with the Autonomous University here in Barcelona. They are experts on fungal treatment. Fungal is also an eco-friendly technology. It helps a lot to reduce the biodegradation. You know, you need to keep the system alive, feeding the system all the time because, you know, they have this lacase and peroxidase enzymes. So you can see here the elimination of analgesics, antibiotics is pretty high. So the situation is really good for them. And that's certainly a very friendly technology. At this moment, we are working different pilot plans. It's not really an operational plan, commercial plan, but it's really a pilot plan working in different spots like a veterinary hospital and other places. So basically, we have the fungal treatment is you have the sludge, you have the fungal treatment, and then the removal of the different parameters. Fungal treatment has also been used as well for elimination, because my area is mainly pollutants for different recalcitrant compounds like metropolol acid, and which is found in many hospital treatments, many hospital effluents, and this has been very well, it worked very well for this. Sorry. So basically, in this part, I don't know how much time I have, maybe 5 minutes or less. Basically, this technologies, membrane, nanofiltration, they are working very well for the elimination of removals. Microalgae technology seems a very good opportunity for many applications. The BAC as a corrosion inhibitor in fracking did work very well in Norwegian. We did work with them in Norwegian and also in the US with colleagues in the US. Hospital wastewaters, they are different technologies and they can be used for this, like fungal treatment, which is a cheap technology and can be applied. So let's go now to a more, also in the same line, the more advanced oxidation and combined processes, like in this one, UV treatment, degradation with UV and combined technologies. In this case, we had UV and H2O2, photooxidation of the same compounds of metropolol in the water treatment and different. In this case, we evaluated several treatments, combined treatments, advanced oxidation, fungi. We wanted to know which was the best setup for elimination of all these chemicals. And we came out, also this was combined with toxicity tests because, you know, at the end of the day, when you do elimination of chemicals and elimination of effluents, you want to know if the effluent water is less toxic than the original water. Otherwise, there is a problem, you understand, basically. So here are the results. You can see here that from these graphs, you can see that advanced oxidation and CAS, and to combine it with conventional activated sludge is the best technology because the toxicity goes down in all cases. In the other cases, the fungi or fungi with advanced oxidation does not work as well as AOP. So AOP is most costly technology, but it works pretty well. It's the best one to combine it with AOP. So basically, what we know that advanced oxidation single treatment together with CAS is the best technology to eliminate these chemicals. Let's go to another example. I'm trying to go fast because it's short in time. This is in a real plant in Toledo, in Spain. We use for elimination of antibiotic-resistant genes together with the Madrid University, Juan Carlos I University. And we were able to eliminate antibiotic-resistant genes in this plant, which is pretty useful. I mean, this is very important. You know, antibiotic-resistant genes is a big problem You know, you have the plan, the tertiary plan, full-scale plan. This is a real plan. And we were able to eliminate with different treatments, advanced oxidation, also with peroxymonosulfate, which is very popular, by the way, nowadays. This plan was able to eliminate antibiotic-resistant genes and antibiotic. In some cases, depending on the technology, photolysis was more efficient for the removal of antibiotic-resistant genes than oxidative removal than other technologies, like photolysis was better than the other ones. So, but one of the problems that we can have with antibiotic-resistant genes is also that in the drinking water. This is a paper from China, where they showed examples that this goes to the drinking water, the genes can go to the drinking water. And here I have a cartoon from a friend from the UK that maybe one day you will go to a restaurant and you will ask for a glass of water and they will ask you, do you have a prescription? Because the water will contain antibiotics. Hopefully this will not happen, but it's something that is in the mind of many people. Removal of microplastics, membrane technologies, they work pretty well, more than 90%. And recently, a review paper published in Stotten also showed that advanced oxidation with zinc O2 and the titanium oxide was very efficient. And also at the end, you get CO2 and water, which was probably one of the most efficient technologies. Also, microbiological, like fungi and bacteria, was applied. And at the end, the last part is also the removal of SARS. We did some work in India together with this colleague there to know different technologies like conventional technologies, conventional activated slides, compared to root zone technology. And the situation was here, you can see the removal rates was not so different one to the other, but we were able to remove different, it was different from each gene. I don't want to go into the detail, but if you are interested, this has been published in the Chemical Engineering Journal. Shows that the removal rate in each technology was different. And this is basically, this is the paper published in the Chemical Engineering Journal. Wastewater treatments may not completely remove the SARS. Wastewater treatment may not remove completely, but the sum of the genes, depending on the gene, they remove the technology is different. They can remove in a better way. So the ORF1 and S genes were more sensitive to the treatment than N genes. So in this particular technology. Then together with a colleague together with the colleague Shadi Hassan in Emirates, we wrote a review paper on the removal technologies. And for instance, composite membranes have seen one of the examples that they can be used for the removal of the virus. And also different mechanisms of membrane technologies with the way they can attach the viruses to the biomass, and they can really help the removal rate. Also, advanced oxidation seems to be very, very useful for this, and it works pretty well for the removal. This is the paper published in Journal of Chemical Engineering, which was
Professor Damia, you have 5 minutes to finish.
This is the end. This is my last slide because I was running. This is my last slide, so it's no problem. This is my last slide. Microplastics can be removed by membrane technologies, as well as by photocatalysis. You know, microplastics is now one of the new problems in the water treatment. Different low pressure membranes and absorption repulsion you can use for different removal of the virus. Composite membranes can also be used for the removal of the virus, chlorination, ozonization. Hybrid processes seems to be also one of the solutions to the removal of many of the chemicals, not only of the virus, but also you have seen before of the pharmaceuticals. So it seems that one of the tendencies now is to use hybridization of membrane processes or to use combined technologies to elimination of the complete removal of all the chemicals and also viruses. I think this is my last slide. So thank you very much. I was a bit fast because the time was limited. Hopefully you got some idea about what the number of things that we are doing, and if you are interested in a specific topic, I can always send you more detailed information. Thank you very much. If you have questions, I will take it.
Thank you, Professor Damia, for this important lecture. We have the chance for 2 or 3 questions.
Hello, Professor Dania. This is indeed
Hello.
a very good lecture, comprehensive and very neat. I saw that you applied membrane technology for wastewater treatment. Now,
Yeah.
fouling is really a serious problem. How did you handle fouling when you used membrane technology to treat your wastewater?
Yeah, of course, fouling is one of the main problems, as you know. And of course, cleaning the membranes, now the new membranes are better than the previous ones, but this is the issue, yeah. Fouling, in the beginning, I remember we had many problems. That was 10 years ago. Now the membranes are better technology, but still you need to clean it up. You need to do some cleaning and changing the membranes. That's, of course, we cannot avoid fouling. It depends on the quality of the influent. If the influent is really very polluted, then fouling will increase, of course, and the type of water. So it depends very much what type of water are you treating. You will need to do the cleaning. That's for sure. So
Okay, thank you very much.
There's no other way. Yeah.
Another question? Dr. Arafat?
Thank you very much. This is Hassan Arafat from Khalifa University. Very interesting talk, thank you. With regards to using reverse osmosis or nanofiltration to remove toxins from wastewater. Now with these, especially reverse osmosis being based on diffusion, solubility, diffusivity through the membrane, do you foresee a risk in the future that there might be some contaminants that might diffuse well through the membrane that we're not concerned about right now, but they might become emergent contaminants in the future? So right now we might be treating feeds and targeting certain pollutants, and we see that we're removing them really well, but there could be things that go through the membrane because they diffuse or dissolve well in the membrane, but 10, 15 years down the road, we might say, well, the membrane is not effective for those, and those are really things that we should worry about. So it's more of a forecasting question rather than what we have now, basically, but it's something that we have seen with other things like boron, for example, in RO. What's your thought on that?
I fully agree with you. In fact, what we did here is a following up target, what we call it. There are two ways to tackle pollutants, target and non-target. This was target analysis. Let's say we look at certain chemicals. But now what we are doing is looking at non-target. Non-target means that you screen everything. Then you can see if there is a peak in your chromatography, in your LCMS. If you see something, maybe now you don't know what it is, but in the future you may know it. So you are right. They can be some pollutants that can diffuse. And we know that for these pollutants it works. I said it works for pharmaceuticals, it works for the examples that I give to you, but I don't know what happens with the other ones. And that's certainly one of the risks, that you can get some diffusion into the system and they can go through. And the best to avoid this is to check, to do the studies with what we call it now non-target analysis. Let's say you check everything which is in your chromatogram, not just the chemicals that you are looking for, you know. So that's, but you are right. This is very important information, and I think we should, all the experiments that we perform today, we should store it in the computer and check maybe in few years if there is any new chemical that it may be a risk for the situation, for the river or for the drinking water.
The last question will be my question. Professor Damia, I'm working with combined treatment processes. Because we are concerned with the cost of these processes, I think there should be some pre-treatment processes before the membrane step, because membranes usually cost a lot for treatment of these pollutants. Do you think that there should be some pre-treatment processes to reduce the cost of such processes? And what are these processes, do you think?
Well, this is also a good question. I think yeah, we need. In fact, when I always give a presentation, I always like to talk about, let's call it expensive technologies like advanced oxidation, and you know, for everybody, everywhere is expensive, but more in developing countries. And then we need to have the eco-friendly. For the reason we did explore the fungi treatment, the microalgae, I think it's very important to have technologies that everybody can apply. So what can we do before the treatment? Well, filtration, very basic things. like filtration or different types of filtration with the conventional filtration and removing what the treatment plants are already doing, a kind of primary treatment, no? Let's say, as doing the best technology possible, the best possible technology. But I think I would like to explore the eco-friendly what I call it eco-friendly. With some of us we call it like fungi, like microalgae that you have. Everybody has in the country different types of microalgae. All these technologies are cheaper than the nanofiltration and membranes and all these technologies and advanced oxidation. And I think we should have both because, you know, not everybody can afford such type of technologies. And I always say it's better to do some kind of treatment than nothing. So it's better to do something than nothing. So don't try to go always to the most expensive technology because, you know, it's too costly. And I think anything that you can do for the removing of the like a primary treatment, like the treatment plants are doing, this is good. Will be, of course, ideal before doing a more sophisticated treatment.
Thank you very much. Thank you, Professor Dami, for being with us in this important lecture. And we would like to thank you also for your journal, which is one of the sponsors for our conference. We will send you some of good papers in order to make some special issue in this journal after the conference.
Thank you.
Thank you very much.
Thank you very much.
Dear participants, and after this, now we should go out. Then after 20
to this session, and thank you for your attendance, and also thank the participants for their effective and valuable presentations, which will include applications of mass and heat transfer processes in chemical industries. We are very much looking forward that this session will be opportunity to discuss and introduce the new developments and innovations in the area of mass and heat transfer. Our first speaker today, Professor Basma from Iraq. Professor Basma, I will hand over the speech to Professor Basma. Professor Basma, please. Okay. لا دكتورة بسمة in hall. طيب. The next speech will be introduced by Professor Amrutha. The title is Review of Multi-Component Adsorption and Isotherms for Multi-Component Adsorption. Professor Amrutha from India, research scholar, MIT. Okay, MIT, Master of Technology at SDTI. His presentation will be about adsorption. So I will hand over to Professor Amrutha, please. Online.
My name is Amrita. I'm from India. I'm a research scholar in MIT, Manipal. So today is my topic is review of multi-component adsorption and isotherms for multi-component adsorption. This is a graphical abstract in which I'll explain it in a brief way. That is, first of all, when we have any adsorption by using activated carbon or any other carbons or any other material as an adsorbent, we'll take it as from outside of it, and then we'll do some studies over removing the multi-component adsorption or monocomponent adsorption, and we'll go through with the theoretical isotherms. And I have in this paper I have listed out for about 10 monocomponent isotherms and about 25 multi-component isotherms. Among 25 multi-component isotherms, I have included dyes, proteins, and heavy metals, and organic metals, non-organic materials, non-organic materials, all other things. Then it is analyzed. So, while coming for the introduction, the thing is, water is most essential part of each and every part of our life. See, water, without water, we are nothing. So, as and when the increasing population is increasing, and even the presence of heavy metals are increasing, according to the surveys, there are millions of people who are affected by polluted water, and they're having severe diseases. The main reason for it is industrialization and urbanization, making the roads, mining, groundwater extraction, and all of the things. So these are the contaminants or the heavy metals which are present in water. And according to this figure, the various diseases caused by heavy metals like mercury, chloride, lead, nitrate, pesticides. Even it causes long-term effects like cancer, bone diseases, fluorosis, diarrhea, and kidney failures, and blood circulation, everything. So it becomes most essential to remove all the particles, that is heavy metals. So as a friend, these are some of the monocomponent parameters, or this is a formulas which I have listed out and have given the significance over it. So these are the formulas. If in case a textile industry or any industries is effluenting or eliminating a single component or single heavy metals, what the thing they have to do is they have to go with the theoretical isotherms, and then they have to find out with the maximum adsorption capacity and prepare with the composites. The thing is, we can go for the activated carbon and other materials like iron oxides, manganese oxides, aluminum oxides, and other materials like silver nitrate. All the filtration, it's just a filtration. Like we should remove all the heavy metals which are present in the water. These are for only monocomponent adsorptions. So next comes the multi-component adsorption. Here, some of the multi-component adsorptions I have listed below. I have given only 5 in this present PPT. But whenever we go for extended Langmuir isotherm, modified competitive isotherm, or Langmuir extensions, the difference is that some of the isotherm models have the interaction coefficients, and some of the isotherms doesn't have any interaction coefficients. They have given the affinity parameters. What is affinity parameter? Whenever I have a 2 or more, or 1 or 2, for example, I'll take lead and chromium, arsenic and fluoride. Whenever it is present in water, whenever we apply some of the adsorbents, there will be affinity towards, for example, activated carbon. Maybe the activated carbon have more affinity towards lead to attract it, or chromium to attract it. All this criteria will be defined by multi-component adsorption. So I have given the 25 multi-component and 10 monocomponent. So what I did is I went on with an experimental analysis, that is prediction of multi-component isotherm models. So these are the modified Langmuir friendly isotherm model. I have taken with the chromium and lead solution, and then I have taken with the activated carbon which was prepared by palm oil male flower plant. Then it was analyzed, and then by using an Excel solver, I have modeled it. Why I have done this? So, because I wanted to know the affinity parameters and also distribution coefficient. How, if in a solution, if I add about a pinch or about this gram of adsorbent, what will be the affinity coefficient? How much it may attract the lead and how much it may attract the chromium? For example, as I told, many industries are effluating or removing all the wastewater to the water, wastewater to the river, and whenever they have some of the effluents like this, for a small amount of materials are enough so that we can come to know about the maximum adsorption capacity of the adsorbent and the quantity of the dosage which we can use for the further treatment. So this model is modified competitive Langmuir isotherm model, and this is extended Langmuir isotherm model. These are the modelings. Here, I have done all the comparison of all the models for the multi-component. That is, some of it is given by the chromium and some of it is by lead. Here, we can notice that modified Langmuir isotherm model for chromium and also for lead. So, the question may arise, like what will be the difference, and all the will be in the same strata, because the thing is, if in case the Langmuir isotherm and Freundlich isotherm, they have different assumptions. If the Langmuir isotherm is
5 minutes, please. 5 minutes remaining.
Yes, sir. Yes, sir, sure.
Okay.
So whenever we go through these isotherm models, if the Langmuir isotherm is good or Freundlich isotherm is good, we will come to know that the assumptions are, we will go through the assumptions. For example, Langmuir isotherm, the assumption is that it is a monolayer. The adsorption takes place in the monolayer, whereas Freundlich isotherm, it gives a value for heterogeneous. So depending upon the background or depending upon the assumptions what we have taken, we can come to the conclusions or the inferences. And these are the most values I got for chromium and lead when I went to the solver by Excel. So the maximum adsorption capacity and K is the affinity towards chromium, the affinity towards the adsorbent. There are different values according to my studies, or according to, I suppose, or I'm doing the experiments with, I have got good value for modified competitive Langmuir isotherm. It strictly depends upon the isotherm model you're following, adsorbent dosage, adsorbates you are using, and everything. And if in case I told you, I said about Langmuir and Freundlich isotherm, it's a basic model for all the models. So if one is dominant or one is good fit, then the other should be analyzed or the assumptions should be taken and considered. And these are the values I got. And thank you. These are some of the references.
Thank you very much.
Thank you so much.
For the useful presentation, fruitful presentation. Actually, we enjoy it. Now we open discussion, only 2 questions. If there is some inquiries or questions. Okay, I would like to ask which basis you select the model for adsorption in case you have multi-heavy metal ions in the medium?
Yeah. Basically, I have concentrated on heavy metals which have more densities. But whenever we are selecting two materials, as you said, 2 components, one should be lighter and one should be heavier, because it depends upon the dominant characteristics. If lead dominates the chromium, the adsorption may replace or the surface complexity may increase. So it depends actually.
Okay, thank you very much. Thank you very much.
Thank you so much. Thank you for the
Okay,
opportunity.
and goodbye. Goodbye. Thank you very much. Now the next presentation will be introduced by Hendrik Kiefer from Germany, from the University of Kaiserslautern. His research focuses on finding new materials for desalination for seawater desalination. As you know, the scaling is one of the major problems in desalination industry. And Hendrik Kiefer is my colleague, and I work with him together several times in Germany. And he will introduce a presentation about new polymeric materials for tubes in desalination industry.
Yes, thank you very much, Wahid. Am I audible?
Yes, please, Hendrik.
Okay, then I will go on. I think you see the presentation right now.
It is clear, everything is
Yes,
clear.
then,
Yeah.
perfect. Then thank you for the introductory words, and hello from myself. My name is Hendrik Kiefer. I'm a PhD student at the TU Kaiserslautern at the Laboratory of Reaction and Fluid Process Engineering. And today I would like to present my research to you entitled Polymeric Heat Exchangers in Seawater Desalination, Impact of Surface Characteristics and Process Conditions on Cleanability. The motivation to investigate novel materials for seawater desalination lies in the continuously increasing demand for drinking water in many regions of the world. The largest share of desalinated seawater is thereby covered by RO and thermal processes like the multi-stage flash distillation and multiple effect distillation. Among the thermal processes, the multiple effect distillation is the most efficient one. And the procedure is, so the process is shown here in detail in this figure. The steam generated in each stage is used in a subsequent stage to evaporate further water, which increases the efficiency of the process. However, sometimes the sometimes very high salt content of the water can cause problems with corrosion and fouling in the process, which is why expensive metallic materials such as titanium alloys have to be used. An alternative class of materials where corrosion is not a major problem are polymers. In addition, these are often less susceptible to fouling. However, the low thermal conductivity is problematic right here. But there are several approaches to compensate this, shown on the right. These include the production of either very thin films or filling the polymers with a thermally conductive material like graphite particles or graphene. In the following, I will present one of each of these approaches for the MED, so the multiple effect distillation, and I will focus on the susceptibility to fouling and the cleanability of the different materials. The materials used were thin polyether-ether ketone films, short PEEK, and polyethylene filled with graphite particles, and these were provided by our project partner Igor Krupa from the Center of Advanced Materials at Qatar University. The results that I will present to you in the context of this talk can be broken down as follows. At first, the studies of the material surfaces, the investigations of the overall heat transfer coefficients and asymptotic fouling resistances with artificial seawater, and approaches to a cleaning in place of the materials after the formation of a salt layer. And thereby the results were always compared with those of the chosen reference material, stainless steel 316L. For the investigation of the material surfaces, roughnesses and free surface energies of the materials were determined. Both properties are examined to interpret the results and to draw possible conclusions regarding fouling. For example, it is known that higher roughnesses lead to shorter induction phases of the fouling process. A non-invasive confocal microscope was used to determine the roughnesses, and the figure here shows the mean arithmetic roughnesses of the investigated materials. And the greatest influence on the roughness is based on the use of fillers. But a plasma treatment, for example, can decrease the roughness again. Pure or unfilled PEEK has by far the lowest roughness. To determine the free surface energies, contact angle measurements were carried out with 4 reference liquids. The free surface energy affects not only the fouling kinetics, but also the wettability of the materials. And for the MED, the wettability with water, which corresponds to a high polar fraction of the surface energy, is decisive. Because if the heat transferring surfaces in the MED are not fully wetted, the performance of the system will drop. The wettability of polyethylene composite is especially problematic here because the contact angle with water is over 90, but however, conditioning the sample with water already results in a significant reduction of the contact angle, and in combination with the plasma treatment, the contact angle could be reduced by almost 20 degrees. Both the heat transfer and the fouling tests were carried out in the apparatus schematically shown here. It consists of a storage tank containing water or artificial seawater, and the fluid is then pumped through one of these two test sections and flows back into the tank, so it's circulated. All relevant temperatures and volume flows, as well as the pH value, are controlled and thus kept constant. The first test section consists of a flow channel with an electrically heated surface onto which foils can be fixed. In the test unit, the peak films were studied, and the control system is selected in such a way that a constant temperature always prevails on the surface. The second test section corresponds to a heat exchanger in which plates can be clamped. The polymer composites were investigated in this section, and in this case, the inlet temperatures and the volume flows are controlled. With the polymer composites, heat transfer measurements were carried out in addition to the fouling investigation, since these are self-manufactured materials. The heat transfer measurements were carried out under laminar and turbulent flow conditions and are shown averaged here. Shown are the overall heat transfer coefficients along with the reference material stainless steel with identical wall thickness, and two observations are worth highlighting here. First, filling the polymer with graphite, so we watch these 2 points here, provides a significant improvement in heat transfer. And the second, this is further improved by plasma treatment. So the polymer composite then achieves a value corresponding to approximately 70% of that of stainless steel. And in order to compare the polymer composites with the peak used, I would like to use a model or show you a model for the falling film evaporation, which in principle corresponds to the process in the MED.
5
It is
minutes,
based on
5 minutes, Hendrik. Remaining 5 minutes only.
Yeah, it is based on the Nusselt correlations shown here. And liquid load was estimated by contact angle measurements of water according to these correlations. And we see the results here. We see the overall heat transfer coefficient over the wall thickness for stainless steel, the composite and two peak variations, so the pure peak in blue, and the crosses refer to the specific materials used in this work with their wall thickness. And we see there's still a performance difference between stainless steel and the polymer composite. But what if we consider fouling, which mostly occur in real processes, fouling? This could further improve the performance of polymers compared to stainless steel. So the thermal resistance caused by fouling, the fouling layer is called the fouling resistance, and this can be taken into account in models for the heat transfer and heat exchanges. For the artificial seawater test system, the components calcium sulfate and calcium carbonate are mainly relevant for the fouling processes, and we have determined the fouling resistance experimentally for peak and the polymer composites. Here at first for peak, pictured are the fouling resistances versus time for stainless steel peak and talcum-filled peak. And overall, the differences are not very large, but we see slight advantages for peak, especially regarding the asymptotic fouling resistance. Also interesting is this drop here in the fouling resistance, which I will discuss in more detail later. And such a drop does not occur for the polymer composites. The results are shown here. On the left, the fouling resistances over time, and on the right as relative heat transfer coefficients compared to stainless steel. So a value of 1 here means that the performance of the polymer composites correspond to that of stainless steel. And here too, the polymer composites have slight advantages over stainless steel, which is in particular evident here. The performance of the polymers compared to stainless steel increase with increasing test duration. And the plasma treatment does lead to higher asymptotic fouling resistances, but we have already at the beginning of each experiment higher heat transfer rates, so that we have slight advantages with a plasma treatment. And this makes the plasma treatment useful in addition to the improved treatability. For the better comparability of all materials, I've added the asymptotic fouling data of the experiments to the fouling film evaporation model, which I presented earlier. And it can be seen that stainless steel in particular is very strongly influenced by the fouling resistance. As a result, the performance difference between the composites and the stainless steel dropped sharply, which was already evident in the experimental data. And however, since the deposit also form on the investigated polymers, the feasibility of cleaning in place is of great interest. Because a simple cleaning in place, for example, can reduce downtimes and hence reduce costs. And pure peak has proven to be a very suitable material for cleaning in place, which can be probably attributed to its smooth surface. And this is because an increase in the shear forces caused by the fluid alone results in the removal of fouling layers. We see here a variation of Reynolds number, so the volume flow, and with higher Reynolds number, we get the self-cleaning effect, so parts of the fouling layer detach again. So consequently, a surge flow alone could lead to a complete cleaning of the surface. The problem is that very high volume flows are usually associated with high pressures, but especially in the case of polymer composites, these are problematic since these materials are brittle due to the high filler content and not very resistant to pressure. Therefore, the phenomenon shown here could not be confirmed for the polymer composites. However, after a fouling period of 100 hours, an acid cleaning cycle could completely restore the initial heat transfer rate, what is illustrated right here. And this already leads me to the conclusion. I've pointed out to you that both the PEEK and the polymer composites are feasible alternatives for the MED and may reduce costs. However, both alternatives have advantages and disadvantages, which I would like to list again right here. The PEEK achieves very high heat transfer rates and is easy to clean, but only if very thin films of less than 50 micrometers are used. And this makes a support structure necessary, so the handling is rather difficult. The polymers, polymer composites, on the other hand, are very affordable, and it is because of the materials polyethylene and graphite. And it is possible to extrude blades or tubes, which makes the handling easy. Nevertheless, the materials are not as pressure resistant as stainless steel.
Thank you very much.
Yes, thank you. I've reached the end. Thank you for your attention, and I'm now at your disposal for any questions.
Thank you very much, Hendrik, for this useful presentation. Actually, this is very interesting for the desalination industry as a new material, new tube materials. Just I would like to ask if about the applicability of such polymers at high temperatures. You know, desalination industry, the working temperature is about 200. Can these polymers work at these temperatures?
PEEK can work at these temperatures. Yeah, it is a high-performance polymer. For the polymer composites, we cannot use polyethylene. That's clearly, but we have another project where we test PPS-EG composites, so polyphenylene sulfide, where we can go up to 150 degrees.
Oh, thank you. Any question more? Okay. Thank you very much for the nice presentation and
thank you, Wade.
Useful information. Goodbye.
Goodbye.
Goodbye. Bye-bye. The next presentation will be given by Ilknur Kukok. Dr. Kukok has received her PhD degree in chemical engineering, department from Yıldız Technical University, Istanbul, Turkey. She is working as an associate professor at the same university, and her research mostly focus in polymeric materials, edible films, incorporated natural additives. Dr. Ilknur, please.
I'm here. My voice is clear. Okay, may I start?
Yes, please. Just start.
Okay, thank you so much. Shared my presentation first. Okay, here. Okay, I'm from the Yıldız Technical University. In my presentation subject, air drying of celery and of drying kinetics pretreatment changes. I'm sorry. Presentation subjects are in a give you a brief introduction, especially why celery, and then food, and then I'll of this work on the expert, give you some deep treatment and drying procedure, and on the modeling that they were used are calculated. The last part will be part. Celery is a low color than with a higher it contains appreciable amount of nutrient, essential oil, and also excellent source of vitamin, vitamin K, potassium, some dietary fiber, and then at this point maybe it's good to say a few things about to health benefit of celery. Celery has widely used the human diet for a long time because it's an excellent source of protein, vitamins, and then other nutrients, while being in fat and fiber or containing cholesterol. So celery has a high volume. We need to some preservation. Drying is one of the alternative preservation. Dries are gaining some popular. They offer just a longer shelf life, stability, and convenience during the transport. And like other way, to find it whole, to use in our meals and etc. And then also, I will do very short explanation how drying food, and drying removes moisture from the food, so bacteria, yeast cannot grow the spoil the food, slow down the action of the enzyme, and not does inactive. That also temperature so the moisture to evaporate. Low humidity allows moisture to move quickly from the food to the air. Air currents speed up drying most air away from food, and drying is an processing, and the applying dishes and some really influences the resulting microbial products. The low of the products prevent growth of the microorganism and reaction, some filtration reaction. Air drying is most widely used method the preservation of food industry, food processing. Okay. In this objective objective investigate the effect of the temperature color characteristic. Our experimental compare drying models and select a model to describe the also compute the effective the activation energy. First of all, we fresh celery were from the local market in Istanbul, and fresh celery washed and cut into were washed with tap water and cut into the pieces. Pieces were about 6 millimeters, and the initial content was determined as a 9.3 kilogram water per kilogram dry matter. The celery samples were divided in a two part. One is the control part, and the other soaking acid solution pre-treatment. And here you can see our drying cabinet, and before started about 30 minutes to achieve steady state, and with three different temperatures, 65 and 75. The air velocity was second experiment at about 30 of celery, and losses were recorded at 10 minutes time interval. And then in a calculate the moisture ratio and dry rate. In the slide you see the MZ is initial moisture ratio as moisture ratio at the, and the ME is at the equilibrium moisture ratio. For the long time, when compared the ME values, we compare the values to M0, ME values is too small, so it's the chance to find are equivalent to MT divided by 0. Okay. We used analysis. We used two static and the determination chi square values by using distribution, and in this is the number of observation, is the number of MR ratio is predicted moisture ratio and experiment. For the best model, we saw the highest R square values and the low T square and RMC values. Okay. The values of effective moisture diffusivity of celery are determined using the second law equation, and the analytic solution of the dissolve analytic state diffusion in a spherical coordinates with the exception of the most migration being by negligible shrinkage called effective diffusivity, and the temperature during the drying time is given equation 1 for a long drying period, and we further simplifies the series is around a logarithmic form, and then when then MR versus the T to get the slope gives us the K. From here is the activation, and the dependence of the effective is generally described by Ahmed's equation, and we can activation energy. Different for nonlinear regression analysis was done mathematical model after content data was transferred into the moisture rate. The technical analysis values are discussion part. As a result, figure present content as a function of trying. You see the in a two temperature in here, but also you see the figures temperature, and then we have a 3 hours drying rate versus time drying for control samples, and then we can say that doesn't show and then our curve temperature, increasing the temperature total get here again from the last figure, and from D I trying time the salary in here we see that drying increases in the increase in temperature, but pretreatment strict adsorption does not have a significant effect on drying period. The three temperature different temperature. So this result agree with this picture.
5 minutes remaining.
Okay. Okay. Thank
thank
you.
you.
Thank you. We have when we made our models for a 55 and sign give us the when we check the R square values is the highest one 0.27, and the lowest chi square and values, and model closest value and Q-tube model for Celsius 65 and 7 is for and when we check is 1 for the 75 Celsius. The highest R square values for it comes from the middle. Similar lowest cheese values and the 5 Celsius is value is smallest for the middle, so we can say that the temperature is middle and Q. In here, the effective distillation energy in here salary in drying between 75 cells is about 1.7 and 3 and minus 10 for pretreated and control samples, and the DF values in temperature, and the values for we get 5 Celsius values, DF values for 50 Celsius, and then again that our is very temperature right in here, but also we energy it was found 32 per mole, and then 1.66 kilo per for pretreated, and then for the range is changing to 70 to 100. So our data is again agreement with the literature. We have a color parameter here. Color parameters as A, and the flash volume, L volumes is about A color to -2 element is for the fresh this range, and the color white celery color parameters samples were closer to fresh samples compared to control samples. For it was observed closest color to fresh in celery dried at used by soaking in street. And then collision air temperature factor in drying of celery. Drying temperature resulted in and pre-treated and very similar drying character. Experimental data were seen for 55 in Küçük model for and 75 Celsius. So effectiveness of the samples were the range 1.2 3 10 minus per second. Energy volumes found 22.30.66 kilojoule per mole. Closest color to fresh celery in dried at soaking in the strict
Thank
acid.
you.
Thank
you very much. Thank you for the nice presentation and useful information. Thank you. Any questions? Any questions? I would like to ask about the effect of temperature on the color as well as on the contents of the product.
Effect of the you asked for color?
Yeah. What is the effect of
Okay.
temperature? How the temperature affects the color of the product?
Okay. Actually, some kind of enzyme, and then increasing the temperature causes some, and the color is changing. Pre-treatment techniques, you have the chance to control this function and the decreasing reaction, so it's keep the color.
Okay.
Now you the reaction getting so the color changing very fast. Explain?
Okay. How this product will be delivered as capsules or tablets or powder, whatever?
It's a kind of smallest pieces, and then when you dry it, it depends on you. You can the tablet, but normally you cut into pieces and then dry and keep them in a some box of how you prefer. It's prepare all of them actually.
Any questions? Okay. Thank you very much for being with us.
Thank you so much.
We enjoy your lecture.
Okay,
goodbye.
Bye-bye.
The last presentation for this session, I mean the first half of the session. The last presentation will be given by Mrs. Noor Amelina Ramli from Malaysia. She is a PhD student having a background in chemical engineering, research interest, her research interest in the field of drug delivery, carrier for pharmaceutical application. As I mentioned, she is a PhD student. Mrs. Noor Ramli, please start.
Okay, can you hear me clearly? Can you hear me? Excuse me, can you hear me, please?
Yes,
Yes,
we can hear you.
we hear you.
Okay.
Yes, we hear you.
Okay.
Okay, just start.
Then I start now.
Okay.
Very good morning to the chairperson and the attendees. I'm Nur Amalina binti Ramli, and currently I'm a student, I'm a postgraduate student from University Malaysia Pahang. Okay, today I'll be sharing with you about my manuscript entitled Evaluation of Mechanical and Thermal Properties of Carrageenan Hydroxypropyl Methylcellulose Hard Capsule. So this is the table of content. There will be 5 sections that I will be present today. And the first one is the introduction of my study, which include the background, problem statements and objective. Second one is the review from previous researchers that will support my proposed study. Third part is the methodology. Detailed results on this scope will be included in the fourth part, and the last one is the conclusion. Okay, background of study. Okay, my study is about the development work of Carrageenan hard capsule that is conducted to offer an alternative to gelatin hard capsule. Okay, Carrageenan is a natural biopolymer which possesses a low mechanical strength when prepared in film. So we propose to incorporate HPMC, which is hydroxypropyl methylcellulose, to reinforce the hard capsule. And at the end of our study, we aim to produce Carrageenan hard capsule with high mechanical strength and improved thermal stability. Okay, problem statement and what is our strategy. So traditionally, majority of hard capsule produced in the pharmaceutical industry is made from animal-based gelatin, which has limiting constraints to those who are vegan and halal food consumers. Thus, our strategy is to develop a plant-based hard capsule made of carrageenan. However, carrageenan has a low mechanical strength and thermal stability, which constrains its application. So in this study, we incorporate HPMC to reinforce the hard capsule. So as being reported by Sun et al., there are limited reports that exist to about the use of HPMC in preparing carrageenan biocomposite for hard capsule application. Okay, research objective and what is the research question? Okay, we want to study the effect of different concentration of HPMC on the mechanical and thermal properties of carrageenan biocomposite film and hard capsule. How do the incorporation of HPMC could improve the mechanical and thermal properties of this carrageenan hard capsule? Okay, so this is the hypothesis. Okay, in the reinforcement of hard capsule, the formation of intermolecular hydrogen bonding network between carrageenan and HPMC is hypothesized as the mechanism to improve the mechanical strength and thermal stability of carrageenan hard capsule. So this cellulose will fill in the void space between the carrageenan matrix. Okay, the literature review. Okay. several reviews of the study of HPMC. So Sun et al. Found that the intermolecular hydrogen bonding will exist between the hydroxyl groups of carrageenan and HPMC, which is able to increase the properties of the hard capsule. By Harimath and Idogdu, they say that inclusion of HPMC can increase the viscosity and lead to higher tensile strength, while Barik et al. Say that addition of 5% of HPMC is proven to improve the TD, the composition temperature of shellac composite, due to mobility restriction imposed by HPMC. Okay, this is the methodology of my study. We start with the synthesis of carrageenan biocomposite. There are also cross-linker, toughening agent, and also plasticizer added in the carrageenan matrix. And we manipulate the concentration of HPMC in the carrageenan, in the fixed amount of carrageenan, from 0 to 1% of HPMC. If the viscosity is meet the desired viscosity, so we then prepare the film and hard capsule, and then we measure the moisture content. If it complies to the standard, then we do further analysis on the mechanical properties and also the thermal properties of the hard capsule. Okay. So this one in the left figure, the presence of HPMC causes the viscosity increase significantly to its highest point achieved at 0.8. And the tensile strength, elongation at break, and also the capsule loop strength are also significantly improved to its maximum at the same concentration. However, despite that, a higher concentration of HPMC in the carrageenan matrix, expecting of agglomeration, and has disturbed the intermolecular interaction between carrageenan and HPMC. Thus, it reduced the viscosity of the biocomposite. At this point, the increase of HPMC is most likely not resulted in higher tensile strength because of the maximum ability of the film to restrain the applied load is reached. Okay, this is the results of moisture content and the disintegration time of the hard capsule. So the increasing concentration of HPMC greatly decreased the affinity of the film to absorb more water. So it enhanced the tensile strength. We can see the moisture content keep reducing, and at 0.8% it is 40%, and it displays the best mechanical strength. And also for the disintegration time, it takes 18 minutes to dissolve, which is within 30 minutes as the commercialized HPMC capsule. Okay, these tables are showing the film, the hard capsule, and also the SEM images of different concentration of HPMC. So we, at 0.8, we can see that the surface is clear and the less opacity of the film. But however, at 1%, the macromolecules are visible at the film surface. That might be because of the highly viscous effect of HPMC. This is due to the deformation forces acting during the polymer chain aggregation. Okay, this is the results from the FTIR. You can see that the OH bonding there, the hydroxyl bond shifted to a lower wave number with increased intensity, indicate the increased intermolecular hydrogen bond. That is the hypothesis of this research, that which created between the materials, which between carrageenan and HPMC. And at 0.1%, it is being weaker hydrogen bonding created. Okay. So this is the results from DSC, differential scanning calorimetry. And at 0.8% of
5 minutes.
TG,
5 minutes
okay,
remaining.
Two slides more.
Okay.
The TG glass transition of the carrageenan film is also shifted by 42%, so indicate the structural modification in the matrix. Okay, mobility restriction imposed by HPMC added in the carrageenan matrix reduce the free volume in the film structure. So the melting point, the melting temperature of this film is also shifted 36%. So the increasing enthalpy of the transition, which makes the film tougher and thermally stable. So this one is from TGA, thermogravimetry. At 0.8%, also we can see that the film is the degradation peak is delayed for about 12% compared to the control. This is the kinetic analysis, and we can see that Kara HPMC 0.8 increased by 43% compared to the control, confirming the positive effect of the HPMC as the reinforcement in the carrageenan film. So you can see that EA is activation energy, which indicates the resistance of its molecular structure to temperature. So as the conclusion as for now, plant-based material introduced in this study, which are carrageenan and HPMC, offer better commercial prospects for wider consumers' preference. So we can see that in our study, the prepared film at concentration at 0.8% demonstrate promising mechanical properties and thermal stability, and hopefully it can be comparable to the gelatin hydroxyl.
Thank you.
Thank you for your attention.
Thank you very much for being with us for this nice presentation. And now we open the discussion. If anyone has any question. Okay. If this is not the case, then I close the session, and there will be a coffee break, and then we'll be back at 14. I would like to welcome you again back to the afternoon session, or the evening session maybe. The next speaker, the first speaker, will be Engineer Obada Dwekat.
15 minutes per لكل محاضرة.
Maximum, okay.
Maximum.
Okay. Obada Dwekat from Palestine. Obada Dwekat, he is engineer, chemical engineer, working as a quality engineer in Al-Rajah detergent factory. He is interested in energy saving using phase change materials. He also and his team improved this work from their graduation project, I think. I am correct. Thank you, Engineer Obada, for coming from Palestine, and we welcome you, and we appreciate your coming here. Please, just start. Okay. Sir Omar here. We would like to thank you very much for joining us. Please start your presentation. Okay.
بسم الله الرحمن الرحيم. السيدات والأساتذة الكرام، السلام عليكم ورحمة الله وبركاته. My research name is Experimental Study of Hydrodynamic Behavior with Monoparticle of Glass Bead in a Three-Phase Fluidized Bed Reactor, Part 1, by Omar Sabah Mahdi, under the supervision Prof. Dr. Jamal Mani Ali and Assistant Prof. Dr. Amr Aziz Abdul Rahman. Sorry.
Just continue, please.
Yeah. Okay. Why fluidization? Fluidization is the operation by which the solid particle are transportation into a fluid-like state by suspended in a fluidizing medium such as gas or liquid or together. The fluidization process is one of the most important interact process that gives direct contact between the fluid and particle, which is important for mass and heat transfer. Therefore, we note that the fluidization process have a wide application, such as industrial, petroleum, chemical, and petrochemical process. The aim of the present work is study the effect of superficial liquid velocity, superficial gas velocity, and particle size on hydrodynamic parameters such as bed pressure drop, minimum fluidization velocity, bed expansion, and phase hold up for a three-phase fluidized bed system. The study of hydrodynamic is important for operation and design the fluidized bed system. The novelty of this study three-phase fluidization and system design, measuring device, and solid phase material. A three-phase fluidization till now has been investigated because of the complex hydrodynamic of and heat transfer are not well understood, such as particle-particle, liquid-particle, and particle-bubble interaction. System design, my experimental work, three-phase fluidized bed reactor, which consists of from fluidizing column, distributor plate, bed material, and measurement device. Fluidizing column is a vertical cylindrical perspex column with inner diameter of 11.5 centimeter and height of 2 meter, which consists of two sections. The first section is test section, which is the fluidization course inside it. And the second section is distributor section of gas and liquid. There we have two types of distributor. The number one, the liquid distributor, and the second one is gas distributor. We put mixing space between this distributor to ensure good mixing between gas and liquid and get uniform distributor for liquid and gas throughout the bed. A present work, this set of tables that show some properties of the fluidizing medium, solid phase, as well as the tower, and also range used for superficial liquid velocity and superficial gas velocity. Design of distributor, the main goal of distributor to ensure uniform fluid distribution throughout the bed and support bed material. Their design must be account for particle iteration, visual and internal component corrosion. Gupta, he suggested in the absence of distributor design criteria for a three-phase, the criteria for design of distributor in two-phase system are used and be acceptable with a concurrent upflow and gas and liquid. Liquid distributor is a perspex perforated plate with 11.5 centimeter diameter and 4 millimeter wide. The plate was drilled with a circular diameter 2 millimeter of 274 holes. The distributor blade was directly designed from the theory of Orpus Cuny and Levenspiel. Gas distributor, air aperture distributor with the 10 centimeter has circular diameter 2 millimeter of 20 holes. This distributor important to generate uniform bubbles circulating across the column. This distributor design was simulated by CFD simulation package to ensure that the distributor pressure technique. The pressure drop bed was measured using 5
I think there is some technical problem. Should we stop or can we continue?
السلام عليكم. الانترنت شويه انقطع.
تفضل دكتور تفضل.
العفو نعتذر.
You have only 5 minutes remaining.
Oh, sorry.
Okay, please.
Yeah. Okay. This is glass bead, which I use glass bead. They use a solid phase. The properties of this bead enhance processing, excellent chemical and heat resistant, thermal stability, low oil absorption. المينيمم fluidization velocity استخدمت معادلة organic equation for two-phase fluidized bed and استخدمت Bikovic equation for a three-phase fluidized bed. طبعا حصلت الريزلت حصلت على العلاقات اللي بين الدلتا بي versus V liquid at constant D particle with varying V gas. And this is the the relationship between this figure shows the relationship between minimum fluidization velocity with superficial air velocity. The increased superficial air velocity led to decrease in the minimum fluidization due to increased gas hold up inside bed. That will be a reduction the minimum fluidization velocity. Bed expansion versus V liquid. The first figure shows the effect of water superficial velocity on the ratio of bed expansion at different value of air superficial velocity for particle with diameter 3 millimeter. The second figure shows the effect of superficial water velocity on the bed expansion with respect to diameter of particle for two-phase flow. Gas hold up. First figure shows the variation in fraction gas hold up and superficial velocity. As the liquid velocity increase, the gas hold up will be decreased. This is due to that the bubbles are quickly driven by the liquid at higher liquid velocity. Since the resistance time of bubble decrease as liquid velocity increase, therefore the gas hold up is decreased. The second figure show the effect of velocity on gas hold up. The gas hold up increase as the superficial gas velocity increase. This is due to when the gas velocity increase lead to increase the volume of gas coming into column. Liquid hold up. This figure show how liquid hold up variation with liquid velocity at various fixed gas and with gas velocity at various liquid velocity. The liquid hold up increased rapidly as the liquid velocity increased. This is due to increase the liquid volume throughout the bed, while the liquid hold up decrease as the gas velocity increased due to increase the gas volume relative to
1 minute only. 1 minute remaining.
Sorry. This is statistical analysis by using response surface model. This effect of variable and model, and effect of variable also and model. Thank you.
Thank you very much for the nice presentation and useful information. And we would like to have some discussion. Professor Zakaria, please.
Thank you, Dr. Omar, for this important lecture. Concerning the fluidized bed reactors, they usually suffer from many disadvantages or problems, such as channeling, gas coalescing, dispersion in the radial direction. All these disadvantages or drawbacks needs some strategy to reduce their effect. Have you thought what type of strategy you make in order to reduce these drawbacks or disadvantages? Channeling, bubble coalescing, and dispersion in the axial direction. Yani the solid phase usually is concentrated around on the walls of the reactor.
Dr. Zakaria, we make, this distributor box, we make some spacing between distributor, gas distributor and liquid distributor to make good mixing, and then will be deriving from this distributor to reduce the bubble diameter, gas diameter like this, and good distributor, a good distribution for fluid inside the fluidized bed.
Dr. Omar, thank you very much for being with us and your valuable time. And
شكرا جزيلا.
And goodbye. Goodbye. Thank you. Bye. Engineer Ubada, please.
Good evening, everybody. I'm glad to be here, and it's my honor to represent my team, Ali Musmar, Taha Karaki, and Dr. Abdurrahim Abu Safa. We work hardly together to achieve this paper about experimental investigation in the performance of phase change material, especially in the solar water heater tanks. Here, we are focusing to increase the efficiency of solar water tanks by using phase change material. As everybody know, Palestine considered one of the rich countries in solar energy, with an average 3,000 sunshine hours per year and an average solar radiation 5.4 kilowatt per metric square per day. These values lead us to utilize and use solar energy to heat water. In Palestine, 65% of people are heating water using phase change material, using solar water tanks. But on the other side, in Palestine, we have some problem in using solar energy due to different reasons. Some of them, that because the great population and growth, the weak infrastructure, and the Israeli occupation policy. And now, let's talk deeply. Energy storage considered one of the most efficient solutions for our problem. especially using phase change material, which have the ability to store a lot amount of energy as sensible and latent heat. Let's talk about our objective. Our objective in our research to design and construct a new solar water tank integrated with PCM tank. This phase change material tank will increase the efficiency and increase the hot water supply time and temperature for the consumer. Second, we are working to simulate the charging and discharging procedure by using variable electric heater power that will simulate the solar radiation in Palestine. Let's talk about our methodology in work. We had design and construct a prototype about 40-liter tank with this main product. We have a hot water storage tank made from galvanized steel. We have an electric heater as shown in figure 3. We have some thermocouples inserted in different places in the prototype to study the temperature in and out from the system. We have different pipes and fittings, and we have the BCM storage tank that we made with our new design. This design will give us the maximum heat transfer rate for the phase change material to completely melt and give us all its benefits. Now, what we use as phase change material? We had used the paraffin wax, a hydrocarbon phase change material, due to different reasons, because it's available, low price, and we have a food grade paraffin wax. Also, it's have an unchanged thermal properties and a huge latent heat of fusion, about 190 kilojoule per kilogram, and its melting temperature, it's around 55 Celsius. Now, let's talk about our design constraint. Our design constraint is the ratio between the phase change material mass and the water mass in the tank, not less than 30%. The flow rate of the water between 0.25 to 0.3 liter per minute, and the heat power, we adjust the electric heat power in around 700 to 900 watt due to different readings in Palestine in the solar radiation. Now, what we study in the test, we study the charging and discharging procedure. What we talk about charging is the process when the heat is up and increasing the temperature of water until the total BCM melt. The discharging process, it's considered when there is no heat source, when sundown, and start a demand on the process so the BCM temperature will get cold. Also, we study the batch-wise system and continuous system. What we mean by batch-wise mean that there is no demand on the device. Continuous system means there is a demand in the device. We have in and output flow rate. What is our experimental outcomes? Experimental outcomes, we had conclude the hot water supply time and temperature, the effect of using phase change material in the system, and the charging and discharging time. Here, we have this figure that shows us the peak hours in consuming the hot water. Mostly in our houses, we have two peak for using hot water from 8 a.m. to 12 a.m. and also after sunset between 6 p.m. to 8 p.m. We are now focusing on another peak. Another peak, we have a high demand with no source of energy. And here comes the idea of phase change material that will cover this gap of demand by reheating the water from the excess energy that she got from the first peak and reuse this energy to heat water and give the consumer more hot water in the evening time, which will prevent him from using electric heaters. Now, let's talk about some of the main results. Some of the main results is during the charging process. We have studied the BCM temperature during charging in batch-wise stage. That means there is no demand on water. We have studied the BCM temperature behavior in 700 and 900 watt. As we can see, in 700 watt, it took about 300 minutes to reach the completely melting of phase change material. But in the system, in the continuous stage, when there is a demand of water, we have around 500 minutes to reach the completely melt of phase change material. Second, we had studied the water temperature during charging process. As we see in table 1, there is a comparison between the conventional system, the traditional system, and the system with BCM. As we can see, we can take 700 watt. It took 250 minutes to completely melt. But with BCM system, it took more time, about 320 minutes to completely melt. And this is the logic. We have more phase change material in the system. This phase change material will take more energy to completely melt, so it will take more time. Now we come to the main result. Our main result is the discharging process. After there is no source of energy, here start the phase change material working. We have a comparison with and without BCM. As we see, we start from the same temperature, and we have now how much time of hot water supply for the consumer. With phase change material, it took more than 300 minutes of hot water supply to the consumer. The conventional system, it took around 200 minutes. So we have 1.5 hours of delivering hot water to the consumer, and this is the advantage of phase change material. Reuse the energy storage at the peak time and reuse it at when there is no sun. Here we study the temperature profile inside the hot water tank. The hot water tank in our prototype have a different thermocouples to study the difference of temperature in the top, bottom, and middle of the tank. As we see, as the logic see, that there is when the hot water is go up, so we have the high temperature of water in TA and the lowest temperature in TC. Okay, خلصت. Now we study a small difference between the flow rate. If we increasing the flow rate, the hot water supply delivering time will decrease. Here we have a comparison in the cumulative energy. The cumulative energy of the phase change material design have more 3,000 kilojoule than the conventional system. This 3,000 kilojoule will increase and heat about 24 liters of water. This is our pilot scale device. We had study and construct. It have two tanks. This large tank have the phase change material with our design and the electric power heater with thermocouples. Our future work. Last week we have construct our new product with 200 liters, and we are simulating the energy by using flat collectors, not electric heaters, and we have a data logger temperature that will read the temperature around the input and output of the system, which will give us a simulating result as the bioscale, and we hope that we are working these days. These are references, and thank you.
He's interested in the solution behavior of multi-component non-aqueous phase liquids. And we'll leave you now, Mr. Patil, to present your work. Please, you have 15 minutes to present your paper. Thank you.
Yes, thank you. I just want to confirm, is my presentation visible to you? I just want to confirm, is my presentation visible? Yeah. Good afternoon, everyone. I am Praveen Gowda-Patil. From MIT Manipal, India. Today, I am going to give a presentation on review on resolution behavior of multi-component.
Mr. Patil, the sound is not clear at your side. Could you please?
Sir, is it clear now? Sir, is it clear now? Hello?
Yes. Continue, please.
Okay. I am going to give a presentation on a review on resolution behavior of multi-component non-aqueous phase liquids. I am from India. This is the graphical abstract of my presentation, where the components are studied in batch and column mode. Few examples are DC, TC, PC, and TDE. Various mathematical models, empirical model resolution, degradation, enhanced resolution. All material related to that has been collected. Coming to the introduction, we know that the contamination of underground water source by NAPL, that is the non-aqueous liquids, spills or leaks is a serious concern for the environment, since these compounds constitute a long-term health hazard for humanity. Underground storage, landfills, and surface spills are the main are one few of the main causes for this pollutant. The spilled pollutant infiltrate into the saturated zone to the garbage zone. We can refer in the figure 1. It will be shown in the next slide. There are two types of naples. They are primarily found in the contaminated sites. They are L napple and D napple. L napple is D napple is a dense non-excessive liquid. L napple is light non-excessive liquid. And they form pools near saturation at bottom of aquifer, which we can call it as D napple. Groundwater pollution will occur in presence of these pools due to the dissolution in the water flowing above or below the pool. Here, this is a figure which shows, this is a typical figure which shows D napple contamination from the ground level till the aquifer is reached. Several earlier studies have studies for natural dissolution in the subsurface made a simplifying assumption of steady source at a constant equilibrium point. And later in 1984, first empirical mass transfer correlation for dispersed oil residues in typical porous media based on experimental data was taken. They also studied mass transfer of petroleum hydrocarbons from oil lamps on top of water surface. In 1985, Cohen and Ryan used a compartmental approach to model the partitioning of BC into the soil, air, water, suspended solids, bios, and sediments. Most of the first napple dissolution models were adapted from chemical engineering literature to design idealized spheres and cylinders in packed bed columns to understand dissolution. They dealt with mass transfer during flow around the spheres and cylinders. Researchers have also proposed heat transfer coefficients and its similar mass transfer coefficients and Peclet number. Researchers model napple dissolution as isolated case that shrinks its dissolution. Imopepol, Powerpepol in 1984 derived widely used correlations for transient fluid dissolution, which used napple saturation as surrogate for the surface area, since it was hard to measure the surface area experimentally. This is a table which shows the various the solubility of the major napple found in groundwater: benzene, dichloromethane, dichloromethane, chlorobenzene, and the respective solubility at 25 degrees centigrade, density at 20 degrees centigrade. Few of them are L-napple, light non-excessive liquids, and the other are dense non-excessive liquids. Single component dissolution studies. Under that, we are going to see equilibrium versus non-equilibrium dissolution. Several contrasting reports have been published discussing whether the equilibrium is possible or achieved during D-napple dissolution, and they have reported small lengths of napple were enough to reach equilibrium. The time required to reach the equilibrium was about 10 months. There are also theoretical studies which show that non-equilibrium conditions could be found for short contact time, large napple blocks, and high velocity conditions. They also proved this experimentally in short columns at high velocity. Powers et al. In 1988 found non-equilibrium conditions existed in 2D tank dissolution experiments. It was also found that most of the evidence non-equilibrium could be explained using models that account for heterogeneity. Though non-equilibrium is possible at high velocity, most of the conditions could have equilibrium dissolution, and apparent non-equilibrium could be due to subsequent 3D dissolution and dissolution of napples can be steady state or transient state. Steady states is for residual saturated napple. The concentration of napple reduces continuously and may exhibit long tails. The transition from steady state dissolution to transition dissolution has not been explored and can play an essential role in remediation modeling. Surface area estimation. The surface area of napple water interface is difficult to estimate. Sodium dodecyl benzene sulfonate is an interfacial pressure to measure the napple water interfacial area. This technique was later extended for residual saturation to others on multi-component mapping. What are the limitations? They are not accurate. Many assumptions are that it provides approximate interfacial area. Compared to use of synchrotron X-ray, microchromography, and interfacial partitioning pressure test, and showed that the values obtained from the test are significantly large. Suggestions could be it could be due to inability of microchromography techniques. Analytical dissolution models. Method to solve advection dispersion equation with dissolution primarily involves Laplace or Fourier transformation. One of the first analytical solutions for DNAPL dissolution is in 1D ground flow was given by Leege et al. 1981. The solution to 3D are complicated for use, and it was developed. Leege et al. 2000 developed an analytical solution for 3D NAPL dissolution using Green's function method. Several others used the Green's method to account for dissolution. McWhorter et al. McWhorter 2001 developed an analytical solution for NAPL dissolution using mass superposition technique. Dissolution of DNAPL with degradation byproduct. Along with dissolution, there are chances that it can yield some kind of byproduct.
Mr. Batit, 2 minutes, please. 2 minutes,
they can
please.
influence dissolution of the parent NAPL. It was also found that daughter products by biodegradation increase PC removal rate by approximate 14 times. Due to shortage of time, I need to just summarize. This is one of the figures which shows that the PC is getting degraded into another two products, trichloroethylene and dichloroethylene. Multi-component dissolution. When more than one component is considered in dissolution study, either in batch or column mode, it can be considered as multi-component dissolution. Several studies have been done using batch and column mode. They have also developed 2D and 3D models. Some studies have used synthetic hydrocarbons, crude oil, diesel oil, and synthetic fluorobenzene. In most of the cases, benzene showed more significant depletion as compared to others. This is table 2, which shows the single and multi-component dissolution case studies using. They have used different organic pollutant and lab studies: trichloroethylene, tetrachloroethylene, trichloroethylene, tetrachloroethylene. They have developed some equations suitable for their study. In the first study, they found that mass transfer functioning coefficient is directly proportional to aqueous phase velocity, and the second, dependency on soil wettability and spatial distribution of NAPL. In third, NAPL saturation reduced from 24.9% to 9.5% in 10 hours. Enhanced solubility, as these compounds are very in density, they go and settle in aquifer. So there are some techniques, enhancement techniques that need to be found. So scientists or researchers have found co-solvent flushing, surfactant, cyclodextrin as one of the techniques to enhance the solubility. In some cases, microbial enhancement is also done. This is a table which shows various chemicals or various methods where enhancement of the DNAPLs or LNAPLs has been done at various conditions. Few of them are, they have used co-solvent, ethanol and water. Some they have studied bacterial. Some they have used acoustic treatment. Acoustic enhancement is done. Similar for single and multi-component. Summary, in this review article, background of NAPL, different types of dissolution in single and multi-component pollutants, a section about partition of NAPL into products is discussed. Also, table 2 to 4 are tabulated to understand various empirical analytical models for single and multi-component dissolution, transport, degradation, partition, and recent advances in multi-component modeling. As shown by many studies cited in this review, substantial progress has been achieved in developing different models. Further study are required in laboratory scale to understand the resolution kinetics of binary as well as ternary component systems. Conclusion is, though the dissolution of naphtha has been studied widely, there are many areas we need to study or we need to focus on. A fundamental method to estimate the naphtha surface area has not been emerged. Further study is required to naphtha source zone detection, modeling heterogeneity, etc. A model that can show the change from steady state dissolution to transient state is yet to be developed. Novel techniques for improving dissolution and natural remobilization can be discovered. The effect of naphtha architecture and heterogeneities on the dissolution must be further investigated. These are my references.
Dr. Vladimir Saranshi.
Yes, I see.
Hello, Dr. Vladimir. Dr. Vladimir from Moscow State University of Land Use Planning Land Use. He's Associate Professor of Advanced Mathematics and Physics Department. He's specialized in mathematical modeling and optimization heat mass transfer processes and reactions in the solid state. I will leave the room for you, Dr. Vladimir, to present your work. Thank you.
Good evening. Excuse me, please. I must download presentation.
Is the presentation with you? You can present from your side, Dr. Vladimir.
Is heat exchange in the processes of welding of rails and hardening of railway wheels. Professor Alexey Lykov and Dr. Vladimir Saranchin, Moscow State University, on land place union. First of all, I would like to say that Professor Lykov is the principal investigator of this problem. The technological processes determining the efficiency of operations on this system presented here. There was a format analysis of thermal conditions during the aluminum thermic rail welding process, such as metal preheating and temperature of liquid metal filled into the mold cavity on the weld and rail metal temperature. Comparison between computed and experimental values of dimensional parameters
could you
of
mute?
weld was carried out.
Asil, could you mute?
Computation of steel surface hardening process by plasma method were carried out. The temperature and its rate on the surface and the bulk of the material will determine it. The thickness of the hardened layer, the structure of the metal, which are formed under different modes of plasma treatment are determined. Computation and experimental data were compared with various hardening regimes. Computation of the thermal conditions in the process of the thermic welding of reveal rays. It will be shown in Fig 2. The temperature of the melt and the rail are given dependent on the coordinate for time duration of the melting crystallization process for K equal 11.5. At the initial temperature of the metal poured into weld equal to 2300 Celsius are shown in Fig 3. In Fig 3. You can see these pictures. Left picture is initial and rail temperature distribution for K equal 11.5 in 35.9. The right picture shown the temperature in melt solid lines, in rail dashed lines in various points of time as measured from the process start. The temperature of start 2300 Celsius. Curve 1 0.2 second, curve 2 10 second, curve 3 58 second. The moment of melting front as time dependent for this parameter is shown in Fig 4, from which it can be seen that the end of rail is melted to depth of 6 millimeters, and the crystallization process ends after 58 seconds. The temperature distribution in the weld in the rail after crystallization of the melt for different times is shown in Fig 5. Fig 5. Fig 4, moving to the melting front, depending on the time, for initial temperature, EK 11.5. The right picture temperature distribution in the weld and the rail after solidification of the melt in various time. Initial temperature 2,300. This mistaken system. It must be right on C, the cesium EK equal 11.5. One curve is initial null. The row of two curve 5.83 the first curve 100
Dr. Vladimir, 5 minutes still remaining. Only 5 minutes.
Yes.
Okay.
Go. Ага. Забыл 25. 25. 25.
25.
Так вылетело.
Only 5 minutes. Okay. Please.
Yes, I see. The next picture shows the rate of cooling of the metal in the weld rail after solidification of the melt. Depending on the temperature, a different distance from the axis of symmetry. Initial temperature 2,800 Celsius, K 35.9 and curve 1 is 1 second to 20 seconds, 3, 25, 4, 30 millimeters. Right picture is show hardness and dimensional characteristic of the weld in the heat affected zone. Conclusions, the theoretical analysis of the thermal condition in the weld and near weld zone in the process of the limited welding of the rails showed the satisfactory correspondence of the computed and experimental values of the dimensional characteristic of the weld of near weld zone. To the process of aluminothermic welding conducted with a decrease in degree of preheating of rails before welding while increasing the temperature of the molten metal poured into the mold in order to improve the structure of the metal and accordingly the strength of operation characteristic of the weld can be applied in practice when welding rails. Plasma hardening of the rail ridges. the sulfur temperature on the non-isothermal cooling diagram of the wheel steel. 2 is represented in next figure. The temperature change in time is given for different specific heat fluxes and times of exposure to a single heat pulse of rectangular shape of the various duration, the values of which are determined from the condition of reaching the melting temperature of the surface. The left picture cooling of the steel surface during hardening by different specific heat flows at different times of its action. Здесь there is heat flow.
Dr. Vladimir, we would like to have the conclusion in 1 minute, please.
Yes. Conclusions. Experimental data on hardening by direct acting electric arc, more high intensity heat flows are realized, and by remote electric arc controlled by magnetic fields, more softer thermal effect, no more extended in direction of the plasma generator relative to the treatment surface presented. When hardening with the direct electric arc use, the thickness of the hardened layers is 1.5 millimeter, and the structure of the surface is represented by 100% matte sheet. And hardening by remote electric arc about 4 millimeters be in structure consisting of mix and matte inside and more plastic component of true stud. This is this is a picture. Left picture is direct plasma hitting. Right, it is remote plasma heated. It is you can see left and right pictures. Properties is hardened layer, micro hardness and hardness is by Vickers. It is photos, pictures, macrostructure of hardened layer.
Dr. Vladimir, thank you very much for the nice presentation and valuable information. And thank you very much for being with us and your valuable time. If there is some questions, anyone would like to ask? Thank you very much. We appreciate your time. We appreciate your time and the useful information. Goodbye. Thank you.
Thank you very much. I am Kachveras and in quarantine.
Thank you. Goodbye.
Thank you. I intended to visit Amman.
Yeah, we are looking forward to visit us in Jordan.